Hi, this is Crew 5. Today I'd like to present about the master assignment MEMS sensor modeling and system integration for the subject Mania 5023 Electronic Design and Microsystem Technology, and presented to Dr. Riza Azri bin Ramli. This shows the wiring diagram which was connected between the Arduino UNO R3 to MPU6050 sensor, and this side shows the MPU6050 pin which is VCC connected to the 5 pin Arduino UNO board, and the ground need to connect to the Arduino's ground, and the SDA pin to the Arduino UNO's A4, and the SCL for A5, and the AD0 connected to the ground also in the Arduino UNO R3. Next we see the circuit setup. This shows the overall circuit connection where we connected with the MPU sensor and to the Arduino UNO R3 regarding the previous slide. Next we see the explanation of the Arduino code. Here in the Arduino IDE, this code initialized the MPU6050 using the I2C library. Inside the setup function, the sensor is configured and the program prints whether the connection is successful. In the loop function, the Arduino continuously reads raw accelerometer and gyroscope data using MPU.getMotion6. The code then converts the raw accelerometer values into millisecond square using the sensitivity constant of 16,384 least significant bits per gravity, and converts the gyroscope values into degrees per second using 131 least significant bits for every 1 degree per second of rotation. Finally, the program prints the values in a label format: ACX, ACY, ACZ, Gyro X, Gyro Y, and Gyro Z. After the microcontroller running the uploaded MPU6050 program, showing live acceleration and gyroscope readings stream over the UART interface. Okay, this shows the 7 plots, which is the 9 millisecond. When off, you can see the acceleration X, Y, Z, and the gyro X, Y, Z. Okay, so we turn off the gyro first. Then you can see the first area is here. Okay, when the X tilt to right, you can see the start from above. When the X tilt down, it start from here. When we move up to above, you can see the Y start from above. When we move down the Y, you can see it decrease. Okay. The Z is a place where it plays in the middle, which represent this one, which is 9 point. The closest unit is 9.73, which represent 9.1. Okay. Then we turn on. Okay. Then we run for the part gyro X, Y, Z. So we turn off the X, Y, Z. This is for the gyro X, Y, Z. When the gyro X go up, it goes up. When go down, it go down. Okay. When it goes down, it goes down. Okay. When this gyro was tilt to the right, tilt to the left, you can see it goes up and it goes down. Okay. The Z is the yellow line. When the Z goes up, because from the gravity it goes up. Okay. When it goes up, put down, it goes to the downside. Okay. When it put to the surface, it goes up and come back to the normal form. That's all. After the code is executed, the microcontroller continuously retrieves sensor measurements via I2C and outputs them to the serial monitor, where the values are interpreted to assess linear acceleration and angular rate behavior. This is the serial monitor. Here we can see the live reading. Then next is the screenshot snippet will be shown here for the explanation. This table shows a snippet of the raw data collected from the MPU6050. We can see that the acceleration Z values are between 9.68 and 9.76 millisecond per second, which is very close to the gravitational acceleration of 9.81 millisecond square. This tells us the sensor was mostly upright and stationary, with gravity acting mainly on the Z axis. Meanwhile, the acceleration X and acceleration Y are very small, between about -0.04 and 0.14, which indicates only minor tilting or small hand movement during the recording. For the gyroscope and the angular velocity, values are also very small. Gyroscope X ranges from about -3.8 to -4.2 degrees per second, and the gyroscope Y and gyroscope Z are below -1. These small negative values shows slight unintentional rotation or micro vibration, not deliberate the motion. Overall, this raw data confirms the sensor is functioning correctly. It accurately detects gravity on the Z axis and shows minimal tilt on X and Y, and registers small rotational noise when stationary. And this dataset will be compared with the Simulink simulation result in Part C laterly. That's all. Thank you.